Hello everyone, welcome to this online course on material science. This is lecture 25 in module 1 on magnetism. So far in previous lectures I have finished the discussion on diamagnetism and paramagnetism, and I took the approach both classical and then went on to the quantum mechanical considerations to understand diamagnetism and paramagnetism. For both dia and para, one thing was common, that we are trying to understand the behavior of magnetic moments of some atom or some piece of solid in the influence of an external magnetic field. So external magnetic field was a crucial input to understand both dia and paramagnetism. But today I want to start a new class of magnetism, which is usually known as spontaneous magnetization. And for that, the crucial point is that no external magnetic field is required, right? So our external magnetic field in this case is zero. And the idea is that even if you don't apply any magnetic field externally, the moments of an atom or moments inside a solid will try to align themselves. Now the question is why they align themselves, or why they try to anti-align themselves with each other. We don't know yet, but I will discuss them at some point. But in this first lecture, I just want to give you the idea is that let's assume for some reason moments inside the solid or in an atom want to align themselves, right? And in that class of spontaneous magnetization, we have three different types. Like the ferromagnetism, we have anti-ferromagnetism, and then we have ferrimagnetism. And just to give you some idea about this ordering in the material, let's assume we have a toy model where our solid or our piece of problem is just nothing but a two-dimensional square lattice, right? And every side has some magnetic moment sitting on it. Now, if you look at these moments, right, which is denoted by these arrows, they are kind of identical. So in this model, every moments are equal in strength. Now, let's say for some reason in this type of material, I don't know, let's say some material here, and then the moments decided to align themselves in this direction, right? So you can see the net moment will be along this direction, and we will have a large magnetization, right? Similarly, the same problem, and let's say here what's happening is that the neighboring atoms decided to anti-align, right? So this one is in this direction, this one is pointing in opposite direction, this one is pointing in the opposite direction. So you can see the nearest neighbors are kind of anti-aligning themselves. And this kind of arrangement is known as anti-ferromagnetism. And then the last one is the ferrimagnetism, where we have a kind of anti-ferromagnetic case where nearest neighbors are anti-align themselves. But the important difference between anti-ferromagnetism and ferrimagnetism is that the moments in different sides are not equal in strength. What happens is that although these two moments are pointing in opposite direction, but they cannot cancel each other, right? But here, if you consider this part of the lattice, the net moment is zero. It vanishes because they are equal in amplitude and they are pointing in the different opposite direction, right? But here, although they are pointing in different direction, the moments don't get cancelled. So that's the kind of material we usually known as ferrimagnetism. Now, to begin the discussion, let's concentrate on the type of ferromagnetic material. And usually I'm listing some of these materials like ferrous, cobalt, nickel, right, gadolinium, and I'm listing some temperature here in Kelvin scale, right? And this Tc is important, and let's define. So for ferromagnetic material, this Tc is the Curie temperature, right? And what this Tc really physically means is that you can destroy the alignment, right? In the ferromagnetic material, moments are aligned, but you can destroy this alignment by increasing the temperature of your sample, let's say. And you have some temperature of your sample, let's say Ts, and then you try to destroy this alignment, and this alignment will be gone as soon as you go above this critical or this Curie temperature. So a ferromagnetic material, you have a temperature which is the Curie temperature, and if you reach beyond that temperature, the ordering is gone and the material becomes non-magnetic. So below Tc we have ordering, and above Tc the ordering is gone, right? And if you have a look at the range of this Tc, so they're different for different materials. Let's say the famous example of ferrous, right? The iron. So iron has like 1043, cobalt has 1394 degrees Celsius. It's quite high, right? So to destroy the ferromagnetic alignment in that piece of ferrous or piece of cobalt, you really need to go this high temperature. So do you understand what that physically means? It means that whatever the reason, we don't know yet why the moments are aligned, but whatever the reason that moments are aligning themselves, let's say for some force is acting between the moments, right? And then that force, we don't know the force yet, but let's say some force is there, and the force is trying to align the moments. And the important thing is that the strength of the force is quite high, because to destroy that alignment, you need to go about like 1000 degree Kelvin, right? So one central point to remember is that whatever the force due to these moments are aligned, it's quite strong inside the solid. And we have to understand the origin of this source, how such force can exist inside a piece of solid, and that will come later. Now let's try to understand that, is there any classical model that should be right, like explain this ordering? And let's try to understand what kind of forces in classical physics can align the moments with each other, right? And so our aim here is to estimate, let's say we want to estimate the dipolar interaction. From classical electrodynamics, you know that when we have two moments, they interact with each other due to their dipole interaction, right? So when we have magnetic dipole moment, and two dipole moments will interact each other. That's nothing new. But the question is, does this ordering has anything to do with this magnetic dipole interaction? That's the kind of thing I want to discuss in this first lecture. For that, let's say we have two magnetic moments, mu1 and mu2. And the distance between them is r. Now, the picture you want to have in your mind is that, let's say we have some moments pointing in this direction. Sorry about that. And then we have some moment in this direction. And the distance between these two moments, well, let's say r. And there is a reason why I'm taking this sort of orientation, where both of the moments are one on top of another, and then they're pointing in the same direction. But the crucial thing is that the energy of these two dipole moments, right, when separated by r distance, is given by a standard result which can be found in the book of classical electrodynamics. So let's say the relation is that the free space permeability divided by 4 pi times the distance cube, and then we have the dot product between the moments, and then we have 3 minus the distance between the moments squared, and then the dot product between the moment and the distance vector times the second moment times the distance vector, right? And now you can see we need to know what is the angle between the moments. Also, we need to know the angle between the moment and the distance vector. But if you consider this sort of orientation where r, so let's say this is your r, right? Some distance vector, and the moments are parallel with this distance vector, and also the moments have the same direction, right? So in a way, if you consider this sort of arrangement, then you know the angle between mu1 and mu2 is 0, angle between mu1 and r and mu2 are also 0. That makes the calculation a bit easier. That's the reason why I am taking this sort of orientation. And for that, you can see this mu1 dot mu2 becomes just the magnitude, and the cos 0, that's 1, so we don't need to write them. And for this part, you will have mu1 magnitude, same angle, so cos 0 is 1, and here you will have mu2 magnitude, r magnitude, and cos 0 is 1, so you don't have to write the unity. And then we have this factor 4 pi r cube. So you can simplify, you can see there is r and r here, magnitude r is squared, they get cancelled with this 3, and here you have mu1 magnitude times mu2, so the magnitude are denoted by mu1 and mu2. We have 3 times then 4 pi r cube, and this is nothing but minus 2 mu1 mu2. This 2 gets and now you can see we have the expression which is minus mu naught by twice pi, and then we have mu1 times mu2. Now usually in magnetic behavior, let's say the moments are due to some atoms, or it could be some electrons, or it could be for anything, right? So anything that has a magnetic moment we are considering here, and let's say they are identical. So we will let the mu1 to be of the order of Bohr magneton. That's always the case, but we want to multiply it with some effective G factor. That's how you model this system, that whatever the moment is, it's kind of G, some effective G factor times the Bohr magneton. And similarly, for mu2 we have G mu b. So if you use this, then the expression for the energy is nothing but mu naught twice pi, and here you have G mu b. Oh, sorry, I'm missing an r cube here, the distance cube. And then so that's it, right? Minus mu naught by twice pi r cube G mu b whole square. let's try to estimate this energy because we know what are these values. So for our problem, let's say the effective G factor we are using here is 1. Mu naught is the free space permeability, right? So that's 4 pi 10 to the minus 7 Henry per meter. We have the distance between the moments inside the solid is of the order of 1 or 2 angstrom. So for this problem, let's say that's 1 angstrom, which is 10 to the power minus 10 meter. Then what about this Bohr magneton? We know the value of the Bohr magneton. This is nothing but 9 point, there is standard value 9.274 joule per Tesla, 10 to the power 24 joule per Tesla. So we have all the quantities on the right hand side and you can estimate the value of the energy. Now, what is this energy equivalent temperature? That's the question we want to ask. So from this expression, we want to replace E by the thermal energy. And the thermal energy is nothing but the Boltzmann constant times the temperature. That's your thermal energy. And we are trying to estimate what is that thermal energy that's magnetic dipolar interaction usually corresponds to, right? So in the expression, you will put E is equal to kBT and all the values are given here. And from that, you will get some value here and try to estimate the effective temperature at which this magnetic dipolar interaction energy really is. And you will see the result is somewhere 1.24 Kelvin. The main thing is that it's of the order of 1 Kelvin, right? But in this table, you can see the ferromagnetic ordering exists in thousands Kelvin, right? And here is 1394 Kelvin. So, and this is 1 Kelvin, right, of the order. So it's kind of 3 orders of magnitude discrepancy. So you can understand there is no way that the alignment inside the ferromagnetic materials of the moments cannot be due to magnetic dipole-dipole interaction, because that's too weak. This interaction energy is somewhere 1 Kelvin, right? But the ferromagnet exists in thousands of Kelvin. So that's a clear indication that any classical attempt to understand ferromagnetism is not going to work, because 3 orders of magnitude discrepancy, it means there is something really very wrong. And you have to completely change your understanding or change your thought process to understand ferromagnetism. And that's what we'll see in the lectures to come. But in this lecture, the punchline is that the ordering of the ferromagnetic material cannot be due to any classical magnetic dipole-dipole interaction. And I think for this lecture, that's about it, and thanks for listening.